Up till now, what we have studied is reflection. Okay, so from now, what we are going to study about is refraction. So before starting with refraction, what is refraction? Acha, have you seen a person appear smaller on a swimming pool? Why is that? A person standing on a swimming pool, when look from above, he looks much smaller than his actual height. That happens due to a phenomenon called refraction. Acha, one more. Have you seen light rays bend through a prism? Even that happens due to a phenomenon of refraction. So start with what is refraction. When a body or when a ray of light, sorry, not a body, when a ray of light travels from one medium to other medium, it changes its direction, and that phenomenon is called refraction of light. So when a light ray travels from travels from one medium to another, one medium to another, it changes its direction. It changes its direction, and this phenomenon of light and this phenomenon is called refraction. Okay, so what do I mean? Suppose this is a water surface. Underneath this surface, water is there, and above this surface, air is there. Now suppose I shine a laser light out here. Okay, this laser light is nothing but incident ray. Incident ray. This laser light, in absence of water, was supposed to go in this direction. Okay, but in presence of water, what will happen? It will bend this direction. Okay, and this phenomenon of bending of ray of light due to change in medium is called reflection of light. Okay, so in the reflection of light, we'll learn few parameters to understand refraction. The first parameter is the normal line. Normal line is nothing but a line drawn perpendicular to the surface. So this surface is called normal line. Okay, incident ray is the incoming ray of light, and this ray, okay, after going into the water surface that changes its direction is called refracted ray. Refracted ray. But the incident ray was called incident ray. Incident ray. Now, like reflection, there was two angles, angle of incidence and angle of reflection. Here also there will be two angles, angle of incidence and angle of refraction. Okay, I is the angle of incidence. Angle of incidence. See, out here remember, angle of incidence is the angle made by incident ray and the normal, and this is the angle of refraction. Angle of refraction. Okay, now what is angle of incidence? Angle of incidence is the angle made by angle made by incident ray, angle made by incident ray and normal. Similarly, what is angle of refraction? Angle of refraction. Angle of refraction is nothing but angle made by refracted ray and normal. Angle made by refracted ray and normal. Okay, that means out here this angle made by incident ray and normal is called angle of incidence, and this angle made by refracted ray and normal is called angle of refraction. Okay, now to understand laws of refraction, we first need to understand few parameters. Okay, so to understand laws of refraction, we need to understand some parameters called refractive index. My question is, what is refractive index? Refractive index. Refractive index is nothing but the ratio of velocity of light in vacuum to the velocity of light in that medium. Ratio of velocity of light in vacuum to the velocity of light in that medium. What do I mean by this? Velocity of light in vacuum to the velocity of light in that medium. Suppose there is a medium. Medium means under is water, above is vacuum. Okay, above is space. Achha. One more thing to note out here. Although theoretically the refractive index of air and vacuum are different, in practice or while solving numericals, air will be treated as vacuum in your chapter of physics. Okay, so the upper surface was vacuum, the lower surface was water. Suppose this is there's an incident ray of light, and this is the normal, and this is the refracted ray. This is angle of incidence, this is angle of reflection. Now my question is, the light that was supposed to travel in a straight line, why does it bend in this way? This is because the velocity of light in this medium is much lower than velocity of light in this medium. Okay, that means the velocity of light is lower. The velocity is supposed to travel straight, no? But due to the velocity of light cannot obtain that speed, the water pushes back, and this light changes its direction. Okay, due to the resistance by water. Okay, so velocity of light in out here is different from velocity of light out here. Okay, so we can say velocity of water or velocity of light in water is something lesser than velocity of light in vacuum. To justify that parameter or to measure that parameter in physics, we use the term refractive index. Use the term refractive index. What is refractive index? Refractive index is measured by mu. Is determined by mu. A refractive index of water given by mu of water is equals to speed of light in vacuum divided by speed of light in water. Speed of light in water. Okay, but speed of light in vacuum is supposed to be 3 into 10 to the power 8 meter per second. And speed of light in water will be found out. See, now one more thing. For every substance in the planet, for every transparent substance in the planet, there is a specific refractive index. That means water has a specific refractive index. Okay, and this specific refractive index will be of for water is 4/3. For glass is around 1.5 or 3/2. So every material or every transparent material has a refractive index of its own. Okay. Now problem is us discussing about laws of reflection. laws of refraction. Laws of refraction. Now, how is this refractive index useful in or useful in determining laws of refraction? See, laws of refraction is given by a law called Snell's law. Snell's law. What Snell says is that refractive index of vacuum, okay, into psi I is equals to refractive index of water into psi I. If you want to generalize this formula, okay, refractive index of medium containing the incident ray, that means let us say mu I. Mu I is refractive index of medium containing the incident ray into sine of angle of incidence is equals to refractive index of medium containing the refracted ray, that means mu of water into sine of angle of refraction, where mu I is nothing but refractive index of medium containing incident ray. Incident ray. What is mu r? Refractive index of medium containing refractive index of medium containing refracted ray. Refracted ray. What is sin I or what is I? Angle of incidence. What is R? Angle of refraction. Sin I is sine of angle of incidence and sin R is sine of angle of refraction. Okay, this is our Snell's law. See, now that we understood Snell's law and how light behaves in different medium, let us further analyze or how light behaves in different kinds of media. So behavior of light in different media, or behavior of light in different media. Behavior of light in different media. What do I mean by this? See, based on the parameter of refractive index, there are two kinds of media: optically dense medium and optically rare medium. So what do I mean by this? See, what should be the refractive index of vacuum out here? What should be the refractive index of vacuum? Refractive index of vacuum is nothing but speed of light in vacuum divided by speed of light in vacuum, or is equals to air. And in physics, vacuum is treated as air, or air is treated as vacuum for solving numericals, or mu of air is equals to mu of vacuum is equals to 1. Okay, so suppose this is a medium. Medium means medium surface. Below the medium there is some water. Okay, there is some air. Now I know, see, average refractive index of water is 4/3 until and unless specified in the question. Average refractive index of glass is 3/2, and this refractive index of different material will be given in the question itself. Okay, so suppose there is water which has a refractive index of mu w, and there is air which has a refractive index of mu air. Mu of air is equals to mu of vacuum, which is equals to 1. A ray of light, if it travels towards the surface, okay, there is a normal. This is the angle of incidence. The refracted ray will bend towards the normal. That means for when the ray is traveling from air to water, or when the ray is traveling from optically dense optically rarer medium to optically denser medium, optically denser medium, the refracted ray refracted ray bends bends towards normal. Okay, the refracted ray bends towards normal. Now what do I mean? When the ray travels from optically rarer medium to optically denser medium, the ray bends towards the normal. So what do I mean by this optically rarer medium and optically denser medium? Acha. See, the refractive index of air is how much? The refractive index of air is 1. Refractive index of water is how much? 4 by 3. So which has greater refractive index? Water or air? Obviously water. So can I say the refractive index of this medium is greater than refractive index of this medium? So can I say this medium or water is optically denser than air? Okay. So if I say refractive index of water is greater than refractive index of air, that means air or water is optically denser than air. Okay. Achha. If water is optically denser than air, tell me one more thing. Where is the speed of light greater? In air or in water? See, what was refractive index? Refractive index was was nothing but speed of light in vacuum divided by speed of light in that medium. So whichever material has greater optical density, the speed of light will always be lesser in that medium. So if refractive index of water is greater than air, then velocity of light in water would be lesser than velocity of light in air. Okay. Similarly out here. Okay. Now suppose the ray is traveling in opposite direction. This is water. Refractive index of water is mu w is equals to 4 by 3. And refractive index of air is mu a, which is treated as vacuum, which should be equals to 1. Okay. Now suppose there is an incident ray. Okay. This is an incident ray, and this is the angle of incidence. When this ray of light enters air, it increases its speed. Okay, and while increasing its speed, it turns away from the normal. So speed of light in this medium is much greater than speed of light in this medium. Okay, so when the ray of light is is traveling from optically denser medium to optically rarer medium. So denser medium. What is denser medium? Denser medium is those medium where diffractive index is more. Denser medium to rarer medium. And what is rarer medium? Medium where optical or where refractive index is less. Refractive index of that medium is less. So when ray of light is traveling from denser medium to rarer medium, light bends away from the normal. Light bends away from the normal. Okay. What you are now going to study is refraction of light through a glass slide. Okay. Refraction of light through through a glass slab. Refraction of light through a glass slab. In this section, there is a glass slab. Okay, the thickness of the glass slab is T. Now suppose there is an incident ray of light out here. Okay, and this incident ray of light has an angle of incidence I. Now the refracted ray inside the glass slab bends towards the normal, and this is nothing but R. And out here again, across this surface, this again bends away from the normal, but this angle is called E. Okay, now what I am going to measure is, suppose I trace out the incident ray, a straight line of incident ray. Okay, what I am going to measure out in this topic is, I'm going to measure out the normal displacement of the light ray, okay, of this much distance, or this much distance of light ray, and this much distance is called shift. Normal shift. Okay, now see out here, if this angle is R, this angle should always be R. Why? This is a straight line and this is a straight line, so this portions an intersection, so R is equals to this R by geometry, so this is also R. Okay, now how do I measure this much distance, or how do I measure this normal shift? Can I draw a line out here? Okay, I can obviously draw a line. Okay, now see, if this entire angle, if this angle is R, how much is the entire angle? This entire angle is nothing but I. See, opposite to this one, so this entire angle is I. So if this entire angle is I, how much is this much distance? This much distance is nothing but I minus of R. So this much distance is nothing but I minus of R. Okay, now let this slanting distance be L. That means the length of this line, I'm taking as L. See, if the length of this line is L, what is the length of this line? The length of this line is nothing but L, or L sine of I minus R, because L of cos of I minus R would be this angle, and this angle is 90. Okay, because we draw a normal, and so L sine of I minus R would be this angle. So I can say that normal shift is equals to L sine I minus R. Here and fine, but I still have a problem. The problem is I don't know the value of L. Can I say L cos R is equals to T? Because T will be given in the question, no? So L cos R is equals to T, or L is equals to T by cos R. If you substitute this L out here, what do we get? We get our equation, normal shift is equals to T by cos R T by cos R into sine I minus R. Okay, what I'm also going to prove is that this line would be parallel to this line. That means this angle of emergence would be angle of equals to the angle of incidence. How? See out here. Let this be a glass of refractive index mu g. This is a mu a. This is also a mu a. Okay. Now across this surface, can I say mu a into sine I is equals to mu g into sine r? I'm simply applying Snell's law. Or mu a sine I is equals to mu g sine r. Okay. Now across this surface, can I say mu g sin r is equals to mu a sin e? So mu g sin r is equals to mu a sin e. So if I divide these two equation, okay, if I divide these two equation, our mu g sin r and mu g sin r would get cancelled, mu a and mu a would get cancelled. So sin I by sin e equals to 1, or sin I is equals to sin e, sin e. Okay, so I can clearly say that I is equals to e. So out here this angle is equals to this angle, irrespective of the refractive index or whatever be the refractive index of the glass. So therefore I is equals to e. Okay. Acha. In the previous topic what we studied is normal shift. Now what we are going to study is lateral shift, or lateral shift of light rays due to glass slab, due to glass slab. Okay, what is lateral shift? Lateral shift is nothing but this much distance, or this much distance is called lateral shift. Okay, so how do we find out this lateral shift? Lateral shift. My question is, how do we find out lateral shift? I found out this normal shift using a formula t by cos r into sin I minus r. So see, this much distance is t by cos r into sin I minus r. What is this much angle? If I can find out this much angle, my half of the problem is solved. Okay. So if I is equals to E, okay, this distance is nothing but, acha, how much is this much distance? If I get this much distance, no, I'll automatically get this much, or this much angle. Okay. So can I say I minus r plus 90 plus r plus name this angle x, plus let's name this angle x, is equals to 180. So I minus r plus 90 plus r plus x is equals to 180. Why? Because angles of a triangle. And if I send this 90 to the right hand side and cancel out the r, so can I get I plus x is equals to 90, or x is equals to simply 90 minus I. X is equals to 90 minus I. Okay. X equals to 90 minus I. So our this angle is nothing but 90 minus I. So if this angle is 90 minus I, how much is this angle? See, this angle plus this angle makes 90 degree, because this is a 90-degree line. So if this is 90 minus I, this should be I, no? This angle should be I. Okay. So this angle should be I. Excuse me, sorry. From this diagram, can I say lateral shift into cos I is equals to normal shift? This is the normal shift. So lateral shift into cos I is equals to normal shift. So lateral shift or LS into cos I is equals to normal shift, which is termed as NS. So in order to find out lateral shift, or can I say lateral shift is equals to normal shift by cos I. See, and what was the value of normal shift? The value of normal shift was T by the thickness of the slab by cos r into sin I minus r. That was the value of lateral shift, and normal shift is nothing but into cos I. Okay, so simply if you find out lateral shift or if you find out normal shift, you can easily find out the other. Okay. Achha, now my question is, instead of one glass slab, suppose in the question they have given multiple glass slab, what do we do? Okay, so that is the case scenario we study out here. Normal shift, normal shift, and lateral shift, and lateral shift due to due to multiple glass slab, due to multiple glass slab. See out here. Suppose this is glass slab 1 and this glass has a refractive index mu g. The thickness of this glass is T1, and instead of writing mu g, let's write it as mu1. Mu1. This is another glass slab which has a refractive index mu2. This is also T2. This is another glass slab which has a refractive index mu3. The thickness of this glass slab is given as T3. Now when a ray of light is incident out here, what will happen? The ray of light will get refracted and again refracted, again refracted, and then it would go out here. What I'm trying to say is there will be multiple refraction. So whatever is the multiple refraction, this line, total line, is the normal shift. Normal shift. This total line is the normal shift. Okay. So what is the normal shift? See, even out here, remember this line will always be parallel to this line, and angle of incidence would always be equal to angle of emergence, irrespective of the values of mu1, mu2, and mu3. It doesn't matter what is the values of mu1, mu2, and mu3. I will always be equals to I out here, or irrespective of the number of changes of medium out here. So normal shift out here. Normal shift out here is given by, it's a very easy formula. Shift due to this glass slab plus shift due to this glass slab plus shift due to this glass slab. Okay. If this is sin I, this is R1. If this is R1, even this is R1. If this is R1, this is R2. If this is R2, this is also R2. If this is R2, R3, and this is also R3. So normal shift due to these three glass slab is equals to normal shift due to glass slab 1 plus normal shift due to glass slab 2 plus normal shift due to glass slab 3. So whenever you are finding out normal shift due to multiple glass slabs, you always add those normal, or you always add the shift due to individual glass slabs. So what is normal shift due to glass slab 1? Okay, normal shift is thickness of 1 divided by cos of R1. Cos of R1 into cos of I. No, sorry, not into cos of I. Cos of I is what? Lateral shift. I'm talking about normal shift. So T1 divided by cos of R1 into sine of I minus R1. Okay. Okay. Now what is normal shift to T2 divided by what is cos R2? This one is cos R2, no? This one is cos R2 divided by cos R2 into sine. What is the incidence for this prism? The incidence for this prism is nothing but R1. So sine R1 minus R2. Out here I minus R1, it would be R1 minus R2 out here. So sine I1 minus, sorry, not I1, R1 minus R2. R1 minus R2. Okay. And what is normal shift 3? Normal shift 3 is nothing but T3, okay, by cos R3. cos r3 into sin r3 r3 or r3 minus I, sin r3 minus, sorry, sin r2 minus r3, not r3 minus I, r2, this is the angle of incidence in r3, sorry, this is the angle of incidence in this medium, and this is the angle of refraction in this medium. So r2 minus r3, sin of r2 minus r3. Okay, so this was the formula for normal shift. Problem is, what is the formula for lateral shift? Lateral shift. Lateral shift means this much distance. This much distance is called lateral shift. This much distance. Okay, this distance is called lateral shift. Okay, lateral shift is equals to lateral shift due to glass slab 1 plus lateral shift due to glass slab 2 plus lateral shift due to glass slab 3. Okay, and what is lateral shift due to glass slab 1? Normal shift due to glass slab 1 divided by cos of I. What is lateral shift due to glass slab 2? Normal shift due to glass slab 2 into cos of, what is angle of incidence in this glass slab 2? R1, cos of R1. And lateral shift due to glass slab 3 is equals to normal shift due to glass slab 3 divided by cos of, what is angle of incidence in this glass slab 3? R2, cos of R2. Understood? So this is our normal shift and lateral shift due to multiple glass slabs. Now we'll study about total internal reflection, and this concept is little bit misunderstood by everyone. Okay, so the concept of total internal reflection. Total internal reflection. Acha. Suppose a glass slab is there or a water air surface is there. Water air surface. By now we know that refractive index of water is greater than refractive index of air. Okay. So suppose a ray of light is traveling in water. Okay. After reaching water, when it goes to air, it will bend away from the normal, no? So this is angle of incidence, this is angle of refraction. So this will keep on happening. Suppose I increase the angle. Okay. Suppose I increase the angle out here. This is water, this is air. And I increase the angle by much more. What will happen? After a certain angle, what will happen? The refracted ray would form 90-degree angle with the normal. Okay. Suppose I increase the angle much more. Suppose this is air, this is air, this is water, and after this angle, this is angle I1. Okay. Suppose I increase the angle some more. Okay. Let's say I2. What will happen to this refracted ray? The refracted ray would bounce back to the water surface itself and follow law of reflection. So out here I2 is the angle of incidence, I2 is the angle of reflection. Okay. Now why is this called total internal reflection? Because after this angle, where the refracted ray grazes through the surface, any more angle that is greater than I1 will get simply reflected back into the water medium itself. Okay. Okay. But why did I say total internal reflection? And what's the condition for total internal reflection? So just write down the conditions. So total internal reflection only happens when the ray of light when the ray of light moves from optically denser medium. Optically denser medium means which has higher refractive index, from denser medium to rarer medium. Okay, fair and fine. But why the name total internal reflection? See, out here, what did I say? The reflected light out here goes like this, and the incident ray goes like this, and refracted ray comes out like this. Out here, I have light something. Okay, suppose I send or 5 watt of incident ray. Okay, only 4 watt of refracted ray comes out. The remaining 1 watt would get reflected back into the water surface itself. Okay, with angle of reflection is equals to angle of incidence. So suppose I say 5 watt of incident ray. Okay, 4 watt of refracted ray and 1 watt of reflected ray. So the intensity of the reflected ray out here is very low compared to the refracted ray. So maximum rays are getting refracted. Achha, intensity of the refracted ray is less. What about the frequency and wavelength of this light? The frequency of wavelength of these both light would be same as the frequency and wavelength of this incident. Okay, now see what happens when I do out here, or what happens when I go like this. What happens is some amount of refracted ray, a reflected ray, comes back to the surface. Okay, I1. But this amount of reflected ray is very less compared to this amount of ray. So suppose 5, I send 5 watt out here. For example, this doesn't usually happen. So actually 4.99, or it has to be lesser than 4, or 3 watt goes to the surface and 2 watt comes out of this surface. So out here, as I'm increasing the angle of incidence, much lesser intensity of light is getting refracted into the other surface, no, and more amount of light is getting reflected into the surface. Okay, so if I increase my angle above 90 degree, if I increase my angle above psi 9, or if the angle of incidence out here is above psi 9, what happens? Total intensity of light gets reflected back. So if I'm sending 5 watt of incident ray, my amount of reflected ray received would be 5 watt. And this is why this is called total internal reflection. Okay, out here frequency and wavelength of light would remain same of these three. The frequency wavelength of these 3 rays are same. The frequency wavelength of these 3 rays are same. The frequency wavelength of these 3 rays are same. What happens or what changes out here is the intensity of light that gets refracted back slowly decreases as I increase the value of I. Okay, and this value of I, where the refracted ray has a grazing, or the refracted ray forms 90-degree angle with the normal line, is called critical angle. Is called critical angle, or I1 is called critical angle. Okay, so whenever incident ray incident ray is greater than, or angle of incidence is greater than, whenever angle of incidence is greater than angle of, or critical angle greater than critical angle 100% of the light, or 100% intensity of the light, intensity of the light gets reflected back into the medium, into the medium and this phenomenon is called total internal reflection. Very good. Now problem is when the incidence angle is greater than critical angle, and critical angle is the angle for which the refracted ray forms 90-degree angle with normal line. So what is the mathematical formula for critical angle? The mathematical formula for critical angle is nothing but mu of water and mu of air. You have to define first. So mu of water into sine of critical angle should be mu of air into sine of 90. Okay, what is the value of sine of 90? 1. Or sine theta c is equals to mu a by mu of water, or refractive index of air by refractive index of water, or theta c is equals to how much? Sine inverse refractive index of air divided by refractive index of water. Okay, or 1 divided by refractive index of water. Okay, now our next topic is escaping light from a point source through a medium interface. What do I mean by that? Let's write down the topic first. Escaping light from a point source through a medium interface. Through a medium interface. What do I mean by this? Suppose there is a medium of interface out here. This is water with refractive index of water, and this is air. And total internal reflection only happens when the ray of light is traveling from denser medium to rarer medium. So suppose there is a point source of light. Point source of light means the ray of light will travel in all directions. Point source of light. Now this point source of light would perform all rays of angle of incidence. Light ray will travel out here, light ray will travel out here, and so on. Light ray will travel out here, light ray will travel out here, and so on. But can I say the angle of incidence out here would be lesser than the angle of incidence out here, would be lesser than the angle of incidence out here? So at certain point, the angle of incidence would be equal to critical angle. So the ray of light would graze past the surface. So for this light, the ray of light cannot escape the surface. So the ray of light will reflect back into the water medium itself. So this ray would reflect back into the water medium itself. Similarly, for this side, suppose this is the critical angle. So all our light that is escaping from the water surface should lie inside this circle. Okay, it should lie inside this circle. You form a circle in the water surface, so all our light can only escape through this surface. This light would escape something like this, this light would escape something like this light would escape something like this. My question is, what is the radius of this circle? What is the radius of this circle? I want to find out the radius of this circle. Achha. Can I draw a straight line out here? So this angle is theta c. So I'm making my diagram neat and clean. And to find out the radius of circle through which the light escapes. This is the point source of light. And this radius of circle is found out by this is critical angle, because any ray of light above the critical angle or greater than the critical angle will simply escape. Okay. Now if this is theta c, can I say this is also theta c? Okay. Now the depth of the point source of light from the water surface should be given as h, or should be given in the question. Okay, this is termed as h. Okay. So can I say tan theta c? Tan theta c is equals to radius of curvature divided by h, or RC is equals to h into tan theta c, or tan of critical angle. Now what is critical angle? Critical angle is nothing but sine inverse refractive index of air divided by refractive index of water. Okay, or radius of curvature, or if I take the radius of curvature, if I solve this equation, if I substitute this theta c out here, so radius of the circle through which the light is escaping is h, which is the depth of light source from the surface of water, into tan into sine inverse refractive index of air divided by refractive index of water. Okay, so just remember RC, or radius of circle, is equals to depth of light source into tan of critical angle. Okay, and from this surface, or from this circular area only, all the light ray would escape, and all the remaining light ray would reflect back into the water surface. Okay. Yeah. Now let's solve a few questions. Okay. Question number 1. In total internal reflection, when the angle of incidence is equals to critical angle for a pair of media, what will be the angle of reflection? Simply, so in total angle of internal reflection, this is water, this is air. If the angle of incidence is like this, and this is critical angle, the angle of refraction would be like this, no? The angle of refraction would be 90 degree. So simply option number C is our answer. Okay. Let's see the next question. If the critical angle for total internal reflection from a medium is equals to vacuum, so the light ray is going from medium to vacuum is 45 degree, then the velocity of light in the medium is. So what the question is saying, there is a medium and this is mu of medium. So out here the ray of light is going from mu of medium to mu of vacuum. What do I know the refractive index of vacuum to be? Refractive index of vacuum is 1, and the ray of light is making total internal reflection. That means the ray of light is making total internal reflection on 90 degree with the vacuum surface, and angle of incidence is nothing but critical angle, and this critical angle is 45 degree. So can I say mu of medium into sine of 45 is equals to mu of vacuum, which is equals to 1 into sine of 90. Sine 90 is nothing but 1, mu of vacuum is nothing but 1, so sine 45 is nothing but 1 by root 2, and mu of medium is nothing but root 2. Now what is mu of medium? Mu of medium is equals to root 2, which is equals to velocity of light in vacuum divided by velocity of light in medium. Now velocity of light in vacuum we know as 3 into 10 to the power 8 meter per second. So velocity of light in vacuum, using these two equations, velocity of light in medium would be equals to 3 into 10 to the power 8 meter per second divided by root 2 meter per second. So our correct option is option number B. Now let's read this question. Which of the following is not due to total internal reflection? Okay. Difference between apparent depth and real depth. Acha. Have you seen a person appearing shorter that is inside a pond? That means if the person is inside a swimming pool or a pond, this person will appear shorter. Why? Because the ray of light that is supposed to travel straight, okay, is bending out here, and the observer out here, this is the eye of the observer. He's seeing the perceived height at this much height. So he's seeing the bottom of the pool at this much height. And this is the difference between apparent depth and real depth. So this much is the real depth and this much is the apparent depth. Okay, we'll go to the calculation and apparent depth and real depth little bit later. For just now, understand that whenever a person is in denser medium, his height becomes or his height appears little bit shorter, and the appearance of that height is called apparent depth, or the real height of the object is real depth. Okay, so mirage on hot summer days. Acha. Mirage on hot summer days is nothing but, see, when you drive a car on hot summer days, what happens? Okay, the lower end of the outhead, the road absorbs heat from the sun, the lower end of the road gets heated up, and this road heats up the air. And light rays that is traveling from the sun travels into rarer medium. So what happens when it reaches critical angle? No, when the light reaches critical angle, it reflects back into the medium, and this phenomenon of total internal reflection causes a mirage. That means wherever a person is driving the car, okay, attempts to see these rays out here, and that phenomenon is called total internal reflection. So when he sees these rays out here, he'll be seeing some deflection of this or whatever is out here, and he'll be assuming that water surface is out here, and that phenomenon is called mirage. Brilliance of a diamond. Have you seen diamond performing white rays or diamond shining very brightly to the point it is white? Why does it happen? Because the light rays inside a diamond reflects back completely into the diamond itself. This is a diamond. Okay, suppose any incident ray, not any incident ray at certain angle, okay, would cross the surface and reflect back into the diamond itself. Okay, so out here, this surface and this surface would appear opaque, and this happens due to total internal reflection. Okay, what is optical fiber? Optical fiber is nothing but information transmitting device. There is a fiber or length of cable that is covered with mirrors, not mirrors, a very this entire cable is nothing but a optically dense transparent plastic. What happens out here is a ray of light goes out here. Now, instead of escaping into the air, the thing is so optically dense is that the total intensity of the light gets reflected back. And out here, total intensity of the light gets reflected back. Total intensity of the light gets reflected back. And out here, it escapes. So this type of reflecting of laser signal is used to transmit information. And this kind of is called optical fiber, or this device is called optical fiber, or this optically dense transparent plastic is called optical fiber. So out here, even this mirage is an example of total internal reflection. Diamond is also an example of total internal reflection. Optical fiber is also an example of total internal reflection. But the difference between real depth and apparent depth happens due to refraction. Okay, out here there is no concept of total internal reflection. The height of the person appears shorter because the observer sees the refracted ray, not the original ray. After this is the incident ray, this is the ray reaching his eyes. The observer sees this ray and assumes that the person is shorter. Now let's see this question. A ray of light is traveling in a transparent medium of refractive index mu, falls on a surface or the surface separating the medium from air. Then angle of incidence 45. So what is happening out here? This is a surface. Below is a transparent medium of refractive index mu. So a ray of light incidence at here at 45 degree just start doing total internal reflection. So at the beginning of total internal reflection, the reflected ray forms 90 degree, no? And when I again increase the angle of incidence, then only total internal reflection occurs. So just at the beginning of total internal reflection, can I say mu of sine 45 is equals to, what is this medium? Mu of air, which is equals to 1. or 1 sine 90, or 1 into 1 because sine 90 is also 1, or mu into 1 by root 2 is equals to 1, or mu is equals to root 2, which is equals to 1.41. Okay, now what happens if I replace this, or what happens if I replace this mu with more optically dense medium? What will happen is this critical angle would get further and further, or decrease further and further. That means with much lesser angle of incidence, the reflected ray or the ray would perform total internal reflection. So out here, if 45 angle or 45 degree performs total internal reflection, that means this mu should be greater than 1.41. Mu should be greater than 1.41. There is only one option which has a mu greater than 1.41, and that is option number C. Okay, acha, remark out here. Remark. By Snell's law, by Snell's law, if we somehow if we increase, if we change the medium, change the medium of incident ray, of incident ray by more optically dense material, by more denser material, then what happens? The critical angle decreases. Then the critical angle decreases. Okay, that means if I substitute this substance by more denser material, this critical angle would further decrease. That means even at 45, total internal reflection would occur. Now let's read this question. This question says that for the given incident ray as shown in figure, the condition for total internal reflection of the ray would be satisfied if the diffractive index of the block. That means just at the start of total internal reflection. So at this surface, total internal reflection should be there. Just at the start of total internal reflection, where would the ray go through? The ray would go through this surface or perform a 90 degree with the normal. Okay, so just at the start of reflection, can I say mu of sine theta? Mu of sine theta is equals to, what is this medium? Mu of air, and mu of air is 1, and mu of air into sine 90, which is equals to 1, or sine theta should be equals to 1 by mu. Okay, now see, this is r. Okay, this angle is 90. This is nothing but 90 minus r, because this angle is 90. 90 minus r is written as r dash. R dash is nothing but 90 minus r. If this is r dash, this is 90. This will also be r, because r plus r dash plus 90 is equals to 180. So r plus r dash is equals to 90. So this is r. Now see, this angle forms 90 degree. So theta is also equals to r dash. No, so theta is also equals to r dash, and 90 minus r. Okay, so from here, can I say mu across this surface? I'm taking Snell's law across this surface. So mu into sine r dash is equals to mu a into 1 or 1. Okay, or sine r dash is equals to 1 by mu. What is sine r dash? Sine r dash is nothing but sine 90 minus r is equals to 1 by mu. And by trigonometry, we know sine 90 minus r is nothing but cos r, which is equals to 1 by mu. So cos r is 1 by mu. The question is asking, what is the refractive index of the block? Refractive index of the block. See, if we apply Snell's law out here, outer. This is our condition 1 where you apply Snell's law at the refractive or total internal reflection surface. If you apply Snell's law out here, can I say mu a into sine 45 is equals to mu into sine r? Mu a is nothing but 1, or sine 1 into sine 45, 1 into sine 45 is equals to mu into sine r. Okay, or sine 45 is nothing but 1 by root 2 is equals to mu sine r. Okay, now I have two values. Cos of r is equals to 1 by mu, and sine of r I have to find out. So if I draw a triangle, okay, I'm drawing a triangle with angle r. Cos of r, if cos of r is equals to 1 by mu, that means 1 mu. That means what is this angle? This angle is nothing but hypotenuse square minus 1 square, or I apply Pythagoras theorem, mu square minus 1 square. Okay, so sine of r is nothing but perpendicular by hypotenuse, or mu square minus 1 under root, mu square minus 1 under root divided by mu. So can I say 1 by root 2 is equals to mu into mu square minus 1 divided by mu. This mu and this mu will get cancelled, or 1 by root 2 is equals to under root of mu square minus 1. So squaring both sides, I would get 1 by 2 is equals to mu square minus 1. If I add 1 to this side, 1 by 2 plus 1, 1 by 2 plus 1 is 3 by 2. 3 by 2 is equals to mu square, or under root 3 by 2 is equals to mu. Option number C. Let's see this question. Transmission of light in optical fiber is due to scattering. What are these phenomena? Diffraction, polarization, multiple total internal reflection. I told you in previous question what is optical fiber and how it works. It works on the principle of total internal reflection, but this device was called optical fiber, and information is relayed by total internal reflection, because 100% of the 100% intensity of the light gets reflected back. Now let's look at this question. This question came in the year 1998, and it's a very good question. Light enters at an angle of incidence at a transparent rod of refractive index mu. That means this is a transparent rod, and the rod is made up of material of refractive index mu. Okay. For what value of the refractive index of the material of the rod the light once entered into it will not leave through its lateral face, whatsoever be the value of angle of incidence. So what is lateral face? This face is known as lateral face. What the question is saying is, suppose I am drawing an axis, whatever be the value of angle of incidence. Okay, this is the angle of incidence. This ray of light will travel out here, and this ray of light would totally internally reflect for whatever angle this is. So just at the start of total internal reflection, what happens? 90 degree or refracted ray goes by 90 degree, okay, through the surface. Okay, because anything, we are just starting the limiting value of total internal reflection. So just at the start of total internal reflection, what happens? The refracted ray goes through 90 degree or forms 90 degree with the normal. Okay, this angle is 90 degree. So let's name this angle R. Okay, and let's name this angle R dash. Okay, from this surface, can I say mu of air is 1 into cos of, not cos, Snell's law is sine of angle of incidence, sine of I is equals to mu into sin r. Okay, from this surface, just at the beginning of total internal reflection, so can I say mu of sin r dash is equals to refractive index of air is 1 into sin 90. Sin 90 is also 1. Okay, and now let's analyze this angle r dash. Can I say r plus r dash plus 90 is equals to 180 angles of a triangle, or r plus r dash plus 90 is equals to 180? So can I say r plus r dash is equals to 90, or r dash is equals to 90 minus r, or out here can I say mu into sine 90 minus r is equals to 1? What is sine 90 minus r? By trigonometric relation, sine of 90 minus r is nothing but cos of r is equals to 1, or cos r is equals to 1 by mu. Okay, now there is another trigonometric relation. We know that sine square theta plus cos square theta is equals to 1. Okay, so I can simply say that sine square 1 by similarity of by using the same trigonometric principle plus cos square r is equals to 1, or sine square r is equals to 1 minus cos square r. Okay, or sine r is equals to under root of 1 minus cos square r. What is r? Cos r 1 by mu. What is cos square r? Cos square r is equals to 1 square by mu square. So sine r is equals to 1 minus 1 by mu square. Now what happens? We substitute this sine r. Out here. Okay. So we get from 1, or bringing this one equation out here, we get sine I is equals to mu into sine r. What is the value of sine r? 1 minus 1 by mu square. Okay. Now let's take this to the new page. Okay. That's right. Now sine I is equals to mu into 1 minus 1 by mu square. Okay, or squaring both sides, sine square I is equals to mu square into 1 minus 1 by mu square. Okay, maximum value of sine square I is equals to 1. Okay, or 1 is equals to mu square 1 minus 1 by mu square, or 1 is equals to mu square minus 1, or 2 is equals to mu square, or under root 2 is equals to mu. So correct option is A. Now I have a doubt. Okay, acha, out here maximum possible value of sine square I. Sine square I is 1. Now I have a doubt out here. Why did I take maximum possible value of sine square I is equals to 1? Okay, see this out here. For diffractive index mu, I have r dash, or r dash is equals to critical angle. Now if I decrease the value of r dash, okay, what would happen? The beam of light would refract from other surface or escape from lateral surface. So suppose I want to keep the value of r dash to be minimum. So to keep the r dash to minimum, what would happen? By triangle law, r dash plus 90 plus r is equals to 180. So if I keep this r dash to minimum, this r would be maximum, and if r is maximum, I is also should be maximum. So for this rod, okay, what is the only thing I can control? The only thing I control in this rod is I. This is the axis. The only thing I can control is I. So I must keep the maximum value of this r. Okay, and to get the maximum value of this r, I have to keep maximum value of I. What is the maximum value of I possible? The maximum value of I possible is 90 degree. And what would happen? I would get the maximum possible value of r, no? That means r would also get maximum. And if r gets maximum, this r dash out here would be minimum. And for minimum r dash, if I get total internal reflection, that means if I now decrease the angle of incidence, if I decrease the angle of incidence, this r out here decreases and this r dash out here increases. So if r dash increases, then the ray would definitely reflect back. So the minimum possible value for this to happen is equals to mu is greater than equals to root 2. Okay, my main point out here is I must keep this r dash minimum. So if I can achieve total internal reflection at minimum r dash, then I can achieve total internal reflection at any angle of incidence. And how do I achieve total minimum r dash? Minimum r dash is achieved by making maximum I dash. So if I make I dash to be 90, okay, then what happens? Okay, then r becomes maximum value, and if r becomes maximum value, r dash becomes minimum value. Now some might have question, what happens if I is equals to maybe is equals to 0? If I is maybe equals to 0, then the ray would escape through this surface, and this is not the lateral surface. The question says the ray must not escape through this surface. Understood? So whatever be the value of I, the maximum value of I 90, which would obtain the minimum value of r dash, and the minimum value of r dash is critical angle for refractive index greater than 2 or greater than root 2. So our answer is root 2. All of you understood this one?